The broadcast is now starting. All attendees are in listen-only mode.
Hello everybody, and welcome to Electronic Packaging Terminology and Design Considerations. I'd like to thank everyone for their attendance and welcome you today. My name is Nick Deberschmidt, and I'm the Director of Content for Electronics Protection Magazine, the co-host for this webinar. Our fellow co-host organization today is Pentair's Schroff brand, and I'd like to thank them for sponsoring this event with us. Before we get started, I wanted to go over a few housekeeping items. First, as you enter the webinar, you are muted. However, please feel free to send any questions for our speaker via the question box in your webinar toolbar. We'll do our best to answer all of your questions at the end of the webinar in the order they were received. You can also message me directly with any technical issues you're having via the chat box, and let us know if you need anything. Also be sure to answer the poll questions as they pop up throughout the webinar, as they will be very helpful. With that said, I'd like to kick off this webinar and introduce our speaker. She is a product manager for Pentair Equipment Protection's Schroff brand retainers, conduction cooled assemblies, and systems product lines. As a product manager, she is responsible for developing and driving Schroff's new product roadmap, as well as supporting and managing the product lifestyle for existing products. Please help me welcome Amy Escobio.
Thank you so much, Nick. And as well as myself on the line today, we have a couple of my colleagues, including Mike Thompson, who is our resident engineering guru, and Christian Ganiger, who is our product manager over in Germany, as well as Mark Kiola, our vertical marketing manager. So we are well suited to answer any questions that you may have at the end of this presentation. So to get started, as Nick mentioned, we're going to be doing an introduction to standards-based design today over the next hour. Our agenda, first we're going to cover a little bit about my company, about Schroff, and then we're going to go into why to design to industry standards, kind of the pros and the cons. Following that, we're going to do a basic overview of standards-based systems, and that includes an overview of the various standards committees, as well as the specifications and the backplane configuration and design methodologies. Following that, we are going to do the systems level thermal management. Okay, so starting with a little bit about Schroff. Schroff is a Pentair equipment protection brand, and it has been a world-leading electronic packaging provider for the last 50 years. It's synonymous with quality and competence in the 19-inch technology, and we manufacture an industry-leading range of standard and engineered enclosures and cooling assemblies. Schroff products and services are the result of a systematic and continuing focus on global needs. The product portfolio includes an extensive range of 19-inch cabinets, subracks, cases, backplanes, embedded systems, and electromechanical components. So why Schroff? As I mentioned, we have over 50 years of experience and are a worldwide leader in 19-inch technologies. We have a reputation for cutting-edge technologies, high-performing quality products, and unparalleled support. We are a founding member of PICMG, and we're actively involved in both the PICMG and the Vita standards committees, contributing both to the strategic direction and to the development of the actual standards. And then lastly, we offer a wide variety of products and value-added services such as lot traceability, DFAR specialty metals, first article inspections, and ITAR compliance. So many good reasons to go with Schroff. Okay, so now to get into our presentation, why design to industry standards? So customers really have two options when it comes to systems. They can either build their own proprietary system, or they can build their system using standards-based solutions. The benefit of a proprietary architecture is that it is, well, proprietary. It can be built specifically for an application and provide optimized results. Additionally, if accepted into the market, it can encourage customer retention since the customer will be committed to the technology. Unfortunately, there's also a number of downsides as well. Proprietary systems are typically developed, built, and maintained by a single vendor, and accordingly, you'll be reliant on that vendor. Over time, if your system is not their highest priority, support may not be optimal, and product upgrades may be slow to arrive. Additionally, due to the development necessary, proprietary systems tend to have long lead times and are typically expensive and rarely feature the latest technology. Lastly, system development requires expertise in many different fields, and typically only the largest companies have all the requisite skills required. In fact, even Tier 1 TEMs and big datacom OEMs consider open standards for the majority or some of their special applications of their businesses. So the pros and cons of open architecture. All market segments are faced with cost pressures, along with the need to keep up with rapid technology changes and network capacity issues. Standards-based solutions reduce the upfront development costs and technological risks when providing the latest proven technologies in a cost-effective platform solution. This model allows for a pay-as-you-grow solution, and it typically uses the latest and greatest technologies within the common architectures. If you plan to deploy your products globally, internationally accepted standards are a must. Additionally, open-based standards platforms provide a large ecosystem of suppliers. The downside, however, is that open architecture systems they have to be designed to a standard. So there is a limit to how much customization a customer can do. Also, since the system is not proprietary, customers will have their option among a number of different vendors with competing technologies or similar technologies. What we find is that many customers opt to do a hybrid, or what we call a modified standard, which is kind of the best of both worlds. These systems are based on the open standard, but customized to meet the customer's needs. These modified standard solutions keep the cost and development times low, but still provide an optimal solution for customers. Okay, I mentioned one of the benefits to an open architecture system is the ecosystem. So working within the open standards community provides solutions and a partner ecosystem. So components can be purchased from a number of different manufacturers, including Schroff, and will still be compatible. These advantages help hedge the risk in today's constantly changing technological environment. I also mentioned lead times. So proprietary systems typically have very long development cycles. Using a standards-based solution, it is no longer necessary to design, build, or even integrate sophisticated systems in-house. In fact, with today's market economics, it actually makes it difficult for the do-it-yourself companies to compete if they are designing their own systems. So in terms of lead times, if we consider a typical proprietary system platform, you would need about 12 to 15 months in hardware development, an additional 9 to 12 months for your particular application development, and then 3 to 6 months for testing and validation. By using standards-based platforms, you can reduce your product's initial development time in half by simply working from pre-validated solutions. Taking it a step further, you can work with our partners within our standards ecosystem to reduce your early product development time down to 2 to 3 months by using their application-ready platforms. So by using all these pre-validated and readily available solutions to build your system application, you can greatly reduce the risk to the evaluation and testing phase. Overall, you can take a typical proprietary design life cycle from 24 to 30 months and actually reduce that down to about 12 to 21 months. As you can see, if you consider the total cost and time to develop, validate, and source proprietary design, the proprietary approach is both costly and time consuming, especially in today's market. Okay. Moving along. So now we're going to do a basic overview of standards-based systems, including an overview of the committees and the various specifications. So as mentioned, the globalization of commercial electromechanical packaging solutions coupled with highly competitive marketing landscapes creates a demand for internationally valid standards. Some of these standards include The International Electrotechnical Commission, or IEC, which defines and maintains the European standards for electronic equipment and mechanical structures. The Institute for Electrical and Electronic Engineers, or the IEEE, is an American institute that defines and maintains the standardization of techniques, hardware, and software. Next, we have the VME Bus Manufacturers Group, which was founded in 1982 and later became the VME Bus International Trade Association, or Vita, in 2005, which champions open systems architectures. And lastly, we have TCI Industrial Computer Manufacturers Group, which is PICMG, that was founded in 1994 and is a consortium of companies that collaboratively develop open specifications for high-performance telecommunications and industrial computing applications. So, starting off with Vita. Vita is an incorporated nonprofit organization of vendors and users having a common market interest in real-time modular embedded computing systems. It is accredited as an American National Standards Institute, or ANSI, developer, and is a submitter to the industrial trade agreements to the IEC. The Vita Standards Organization provides its members with the ability to develop and promote an open technology standards. So Vita's mission includes not only promoting VME Bus, but promoting the very concept of open technology. Vita's continuing goal is to unite manufacturers and users through the acceptance and implementation of open technology standards, including VME, VME64, VME64X, VXS, and VPX. And we'll go through each of these later in the presentation. Next, we have the PCI Industrial Computers Manufacturers Group, which is also known as PICMG, and that is a nonprofit consortium of over 250 companies who collaboratively developed open specifications for high-performance telecommunications and industrial computing applications. So PICMG was founded in 1994, and its original mission was to extend the PCI standard from the PCI Special Interest Group for use in non-traditional computing markets such as industrial automation, medical, military, and telecom. With over 250 members, PICMG has a strong expertise in electronic, mechanical, packaging, and thermal design, high-speed signaling and simulation, and software and high availability applications. With the advent of fabric-based transports, PICMG specs have continued to evolve. This has resulted in a series of specifications that include the compact PCI, advanced TCA, and many others. And we will be going through those as well. Here we can see both the Vita and the PICMG specifications and how they have evolved from the original VME and compact PCI standards to the very latest VPX, compact PCI serial, and ATCA specifications. And this is our perception where each of these specifications are within their life cycle. As you can see, compact PCI serial is still in the launch phase with limited awareness. It's growing, whereas ATCA, MicroTCA, VPX are all in the growth phase, and ATCA is a mature technology. Okay, as promised, now we'll go through an overview of each of the standards. The VME Bus was the first standard from Vita, and it was finalized in 1984, especially for process control and real-time applications. A couple facts about it. VME boards conform to the IEEE and IEC standards, and they come in both 3U and 6U heights. VME Bus supports a maximum of 21 slots in a single backplane, and it features a multi-processor system, so you can have more than one master possible. It has an asynchronous bus, so no clocks are used to coordinate the data transfers, and addressing can range between 16 and 32 bits. It supports bandwidths up to 40 megabytes per second and has a backplane that is split into two sections, so the J1 and the J2 section. The J1 includes 16 signaling lines, the address lines, control signals, and has 5-volt and 12-volt power supply. The J2 section includes 16 lines, like J1, but it also includes additional addressing lines and user-defined functionality. Moving along to VME64X, in 1997, Vita Standards Organization, or the VSO, adopted a superset to the VME64 standard. This new standard is called the VME64 Extensions, or known in short as VME64X. And it adds new capabilities such as a new 60-pin connector family, a 95-pin TO-JO connector, 3.3-volt power supply pins. It supports geographical addressing and has higher bandwidth bus cycles, so up to 160 megabytes per second. It has 141 more user-defined I/O pins and rear plug-in units, or rear transition modules. It also supports live insertion and hot swap capabilities, has injector and ejector, locking handles, support for electromagnetic compatibility on the front panel, and it has some ESD features, or electrostatic discharge features. It's important to note that all legacy VME and VME64 modules are forward compatible to the VME64 spec, backplanes and subracks. That means that the older bus modules can be plugged into these newer systems. Also of key importance, this VME64 actually increases the bandwidth by about 4 times versus the previous VME specification. Next, we have the VXS, which stands for VME Bus Switched Serial. Some key features of VXS include improved fabric capabilities up to 1 gig Ethernet. It supports switched serial fabrics over a high-speed connector, including PCI Express, Rapid I/O, Star Fabric, and InfiniBand. It includes switched fabric technologies for multi-point high-speed data transfers up to 10 gigabits per second. There we go. And it is unfortunately limited to the 6U form factor. And lastly, for our Vita specifications, we have VPX. So as I mentioned, it's the latest generation for Vita for high-speed switching, or high-speed serial interconnect. And VPX stands for Versatile Protocol Switching. It was specifically aimed at rugged military applications. And with the high-speed dense connector, this architecture has a significant advantage of having a large number of rear I/O pins, supporting either high-speed serial or parallel. Some key features of this technology include that it's a similar mechanical form factor in that it comes in both 3U and 6U formats. It has support for PMC and XMC per the Vita 42 standard mezzanine cards. It has 7-row high-speed connectors rated up to 6.25 gigabits per second. It comes in both air-cooled and conduction-cooled versions. And unfortunately, the only downside really is that there is no backwards compatibility with the other Vita standards. So it's kind of a standalone solution at this point. So applications, VME and VME64 are applicable in many different markets and applications, including industrial controls such as factory automation, robotics, and automotive. Defense applications like battlefield control systems, like radar control systems, tanks, etc. Aerospace, including avionics and fly-by-wire control systems. Transportation, such as railway control, smart highway systems, etc., as well as we see some applications in medical and general electronics. Okay, moving along to the PICMG specifications, we're going to start off with compact PCI. Compact PCI was developed in the mid-1990s and was updated again in 2001. It is electronically a superset of the desktop PCI with a different physical form factor. It is supported by a large group of suppliers covering a wide range of products from components all the way up to complete systems. And the next migration step up from Compact PCI was in 2009 with the release of Compact PCI Plus I/O, and that's the PICMG 2.30 standard. And it happens to be backwards compatible with the Compact PCI standard. The Compact PCI Plus I/O offers modularity, robustness, and economic efficiency of the Compact PCI, but it adds fast serial data transfer, all within the same 19-inch standard environment. The Compact PCI plus I/O is ideal for users who either have the original Compact PCI parallel equipment or still have the need for the parallel bus structure but want to migrate or have a need for high-speed serial connections as well. And lastly, the latest evolution of the standard is complete with serial interconnects, and that is the release of the Compact PCI serial .0 spec. Okay, starting off with Compact PCI, it's based on a Eurocard 3U and 6U form factor and supports 19-inch mechanics. Compact PCI provides a passive backplane up to 64 bits and 66 megahertz. It connects the system slot or the CPU up to 7 peripheral slots or devices or more with bridges. And the original architecture is based on a parallel bus, which connects the system slot to the peripheral slots. The backplanes are available in 1 to 8 slots. However, it is extendable by bridges up to 21 slots. Compact PCI features vertical card orientation for efficient cooling and positive card retention with front metal panels. It has user I/O connections for a user I/O connections on the front or rear of the module, and has stage power pins for hot swap, and it's available in either 32 or 64-bit versions. There are, however, some disadvantages, and those include slow data transfer rates. It only goes up to about 133 megabytes per second. And like VME and VME64, it has parallel bus structure, so it is limited. It only supports one single protocol, which of course is PCI, and it only has single master capabilities. And of course, it is limited to 8 slots, as I mentioned, without bridges. Up to bridges will take you up to about 21 slots. So I mentioned parallel and serial bus structures a little bit. I thought I'd go through that a little. VME and we just mentioned Compact PCI both have parallel bus structure backplane. So only one board can communicate at a time, and it tends to be a much simpler design architect. Data transfer rates for parallel bus architecture have increased from 8-bit to 16-bit to 32 to 64, but 128-bit is not practical due to the addition of pins required and the size constraints. So the next generation of systems, such as PICMG, the VME64X, the VPX, and Compact PCI serial, actually utilize a serial bus architecture rather than parallel. With the serial bus, you get full bandwidth between each board via a direct connection, and you can achieve higher data transfer rates. And with this point-to-point routing, all connections can send and receive information simultaneously, which allows you to get full bandwidth between each board. So as mentioned, Compact PCI plus I/O, which is the PICMG 2.3 standard, is a sub-specification to Compact PCI, and it creates a smooth migration path from Compact PCI to Compact PCI serial. It uses a serial interface standards like Ethernet, PCI Express, SATA, and USB without the need for switches or fabrics, and it is backwards compatible with legacy Compact PCI systems. It features a multi-processor capability with operating systems such as Windows or Linux, and like the Compact PCI boards, it conforms to the IEEE and IEC standards in both 3U and 6U heights. So the latest specification in the Compact PCI line is going to be Compact PCI serial, and it is based exclusively on serial interconnects, and it features a new high-speed connector. Like Compact PCI and Compact PCI plus I/O, it is compliant with IEEE mechanical dimensions, and the boards conform to the same standards in the 3U and 6U heights. It supports multi-protocol capability, including PCI Express, Gigabit Ethernet, USB, and SATA, and also has multi-processor capability with Windows or Linux operating systems. It supports 12-volt power and has a rear I/O. In terms of the mezzanine cards, it supports PCM and XMC interoperability, and it has an optional hot swap and IPMI support. So lots more functionality and speed than the previous versions. Okay, Going a little bit deeper into compact PCI serial, it is available in both star and mesh architecture. The star architecture is for the PCI Express and the serial rapid I/O, SATA, and the USB. One slot can control up to 8 peripheral slots, and no bridges are required. So switch fabrics or no switches, switch fabrics, or special backplanes are required. It has one dedicated PCI Express fat pipe for high-end applications. Otherwise, all the other slots are identical. And for meshed architecture, it does support full mesh architecture for Ethernet. Up to 9 boards can be fully meshed, and likewise, no bridges, switch fabrics, or special backplanes are required. The Ethernet is based on 10, 1000, or 10 gig-based T standard, and it's optimized for symmetrical, multi-processing, and redundant systems. So some applications for compact PCI plus I/O, and compact PCI serial. They can be used in a wide variety of industrial control telecommunications applications. Industrial automations applications such as factory automation and robotics. Automotive applications such as railway controls and entertainment. And lastly, we see it often used in test and measurement applications. In fact, kind of cool fact, compact PCI was actually used on the latest Mars rover Curiosity. Pretty cool. Okay, moving along to advanced TCA, like the original ATCA spec was released by PICMG in 2002. And like compact PCI serial and VPX, it features a serial data communication. Initially, it was targeted at the telco industry. However, nowadays, it's used for wireless, data centers, and military applications. And it's typically DC powered. However, AC versions are also available. Some key features of ATCA are its high availability. In fact, it has redundant modules, hot swappable FRUs, etc. It also has remote management and monitoring, multi-protocol capability, so it's compatible with PCI Express and Ethernet, SATA, Rapid I/O, Star Fabric, etc. And it has a multi-processor capability with Linux operating system. And most importantly, probably, is its very, very high data throughput. So here's kind of a breakdown of the various shelf elements in advanced TCA systems. So I mentioned redundancy. You'll notice that there are redundant shelf managers here at the bottom. We do have redundant fan trays, and this particular example is push-pull cooling. So we have one at the bottom and one at the top. We also have redundant power entry modules. So ATCA systems are supposed to be available 99.999% of the time. That equates to, I think it's less than 3 days downtime in a whole year. So very, very reliable system. Okay, ATCA mezzanine cards are defined in 6 sizes. They come in single and double modules, and each of those come in 3 different widths, which is interesting because the advanced MC specifies them, or they're defined in the advanced MC specification as heights. So it's kind of a little counterintuitive. But each of those are available in compact, which is 3 HP, mid-size, which is 4 HP, and full-size, which is 6 HP. Advanced TCA is the interface for the RTM, or rear transition module. There are 3 types of boards for ATCA. There's the hub board, the mesh board, and the node board. And the type of these boards dictates its functionality and where it can be installed within the chassis. So the hub board supplies switching connective boards in the shelf, and it can only be installed in a designated hub board slot. The mesh board, or the mesh-enabled board, can connect directly to all the other boards in the shelf, and it can be installed in any slot. And then lastly, the node board, which can be either single, dual, or many star connections, can only be installed into a node slot. Okay, the main goal when developing ATCA specifications was a scalable architecture which balances both capacity and cost. A secondary goal was an alternate solution to the parallel bus structure on the backplane. because the parallel bus structure limits the data throughput. Advanced TCA backplane is the first backplane which is designed based on an open standard which supports package-based architectures or switch fabrics. There are several topologies options available which support 1, 2, or 4 ports per channel or links between the slots. In a dual star topology, all slots are connected with a star, so on which a fabric switch is placed. A second switch assures the redundancy, which is important to ensure the system availability. So if you have a second switch in there, it's going to be a dual star. All slots communicate with each other via these switches in the hub slots. At a higher demand of power, a second group, yep, that's the dual star. So here, I actually didn't even show the dual star. This is just going to be the dual star solution here. And then kind of taking that to the highest level of performance, we have the full mesh configuration in which every slot is directly connected to all the other slots. So without capacity repressive fabric switches, the data bandwidth can actually reach more than 2.5 terabits per second. So here we have the fully meshed backplane. Okay, ATCA systems always have a dedicated shelf manager, management controller, or SHMC. The purpose of the shelf manager is to monitor and control low-level aspects of the ATCA boards and other field replaceable units within the shelf. The shelf manager has several key functions, and they include watching over the basic health of the shelf and reporting anomalies, taking corrective action when needed. It also retrieves inventory information and sensor readings. It can receive event reports and notification of failure from boards and other intelligent FRUs. It manages the power and the cooling. And lastly, it has electronic keying. So it actually has a capability to manage the interconnects of the resources in the shelf. Shelf managers are available in both bus or radial PICMG configurations. Okay, there has been an increasing demand for power and cooling for ATCA boards, and the next generation of ATCA boards will continue this trend. Luckily, the latest ATCA chassis are ready and available from leading manufacturers to meet this market demand, and these latest ATCA chassis support greater than 400 watts per slot cooling, and they have a 40 gigabit per second bandwidth backplanes. Next, we're going to move along to MicroTCA. The MicroTCA specification, denoted as MicroTCA.x, is a new series of PICMG specifications that take the extensive knowledge and practices developed with advanced TCA and apply them to a smaller form factor. So MicroTCA, the original specification, was launched in 2006, but since then there have been several DOT standards released focusing on ruggedized applications and the physics community. So I mentioned MicroTCA.0 was released in 2006, especially for the telecom and edge access networks. Like ATCA, MicroTCA is it uses advanced MCs, which are interchangeable between advanced TCA and MicroTCA. It is available in single star and dual star with up to 40 gig backplanes. It also has that high availability, so 99.999% availability with full redundancy. It supports the same data transport mechanisms defined in the advanced MC subspecification, so it supports the PCI Express and advanced switching, gigabit Ethernet, storage interface, and serial rapid I/O. However, no rear I/Os are available, so the power input and all the modules will be inserted from the front side. And the specification defines a powerful carrier and shelf management system, as well as 80 watts per slot in the NEBS environment. MicroTCA uses the management structure of advanced TCA with the latter's defined shelf and system management and the carrier management of advanced MC carriers. For MicroTCA, however, a new module is developed in the advanced MC form factor, and that new module is the MCH, or MicroTCA carrier hub, which performs both the carrier management and the fabric functionality. So MicroTCA.1 spec includes 3 main features beyond the basic spec. So it was really designed for higher shock and vibration levels. The front panels have flanges and retention screws to fulfill the higher shock and vibration demands, and it can withstand extended temperatures. MicroTCA.2 spec was specifically designed for outdoor telecommunication applications, military air, land, and sea applications, which require ruggedized conduction-cooled clamshells with air-cooled heat sinks. So these are really they're ruggedized and hardened, and they're to be used in air-cooled applications. MicroTCA.3 allows for hardened conduction-cooled assemblies. So like the .2 specifications, it was designed for outdoor telecommunications, military air, land, and sea applications. It features conduction-cooled heat path, so heat actually transfers from the hot spots through thermal paste to the clamshell and then through the card lock to the chassis. And the spec also supports second-level maintenance. And then lastly, we have the .4 spec. So today's physics community has been using VME. However, they have decided to use ATCA and MicroTCA in their next generation of systems. The main reason for the change is because of remote management and failure detection of FRUs, such as the fans, the PSUs, and the blades. This specification was developed to meet the unique needs of the physics community. So some general applications for ATCA. The primary application, as I mentioned, is really telecom carrier grade applications such as central control offices or central offices. However, the secondary application includes communications such as internet and phone traffic, video on demand, entertainment systems, data encryption, modular servers or blade servers and data centers, modular computing for medical, industrial automation, and military applications. MicroTCA specification is also tailored to meet the telecom market. However, because of its serial architecture and its smaller form factor, it's also suitable for other markets in which high data throughput and a small form factor or scalable architecture is necessary. So think medical technology, security systems, industrial automation, defense systems, traffic control, or image processing type applications. Okay, the last portion I'd like to cover is system-level thermal management. So as we all know, when designing a system, there are several factors that need to be considered in order to manage the heat. The key factors really that impact cooling performance include the airflow, impedance, the thermal load, the blade thermal profile, and height. So when working with Schroff, at least, you can contact us, and we have a whole team of applications engineers and design engineers that can go through all of this with you to find an optimal solution. Also critically important is the direction of the airflow when cooling blades. So Schroff offers top to bottom, front to rear, left to right, right to left, front to left, and front to right. So many, many different options in terms of the direction of the airflow. And once again, our team is experts on this type of thing with the cooling, so they will find the optimal solution for any specific design or application. I mentioned this briefly earlier in the presentation, but when cooling, both the volume of the air as well as the air pressure are key metrics to be considered. Accordingly, we offer systems with a push, pull, and a combination of push-pull fans to provide cooling up to 450 watts per slot. And then originally, 200 watts was the design goal for the ATCA specification, and over the last 10 years, the design goal for cooling has more than doubled and is met by our most recent products. Here on this chart, the CFM is calculated by assuming that the air density is 1.6. We multiply that by the power in watts and the device temperature, and divide by the device temperature rise to get the CFM. So this chart can kind of be used as a general rule of thumb when figuring out how much cooling would be required for any particular application. And that's all I have for you today. I guess we can open it up now to some questions.
If anybody has any questions, feel free to post it up in the question box. We'll also run a few polls here. Get those started as well. And if one that is, you're not sure of Amy, we can have one of the other folks answer one as well.
Sure.
Well, it looks like we're not getting any direct questions here. So I think if no one has anything, I'd definitely like to thank Amy for speaking and giving a good presentation today. And certainly if anybody has any questions they'd like, if something came up after they saw the presentation, they can certainly get a hold of Amy or me, and we'll do our best to get them answered.
Excellent. Thank you so much, Nick, for the opportunity to let us host this as well, and thanks to everybody for calling in. And, definitely contact us if you think of any questions then.